Hi, this is Dr. Sridhar, working as professor in Institute of Aeronautical Engineering, Hyderabad. I'm back to a new video lecture on equivalent series and parallel networks of various passive elements in the electrical systems. Just for a while, think what are the voltage and current relations of various passive elements. In my previous videos, we have elaborated with some suitable examples what is the relation between voltage and current across through the various passive elements, like what is the relation of V and I of resistor R, what is the VI relationship of inductor L, and what is the VI relationship of capacitor C. Just to try to recollect the VI relationship, because with the help of that VI relationship only we are going to establish the resultant value of the resistance if the circuit is having more than one loop. So this is Ohm's law. I is directly proportional to V, or V is equal to I into R. This is the Ohm's law statement. This is a fundamental law. Definitely this law is also helpful for us to determine the equivalent of series and parallel electrical networks. So same thing, this is across the resistor, the relation is, current relation is I is equal to V by R, and voltage is nothing but I into R. This is the inductor. Inductor, the voltage drop across the inductor is equal to L into di by dt. So I is nothing but the current flowing through inductor. And if you are rearranging that equation, I becomes 1 by L times of integration over V into dt. The relations, the R and L relations, that is the relations of VI of resistor R and inductor L, are more or similar to same. And one more is capacitance C. So the voltage across the capacitor, whenever it is allowing some current through its plates, the voltage is equal to 1 by C integration over I into dt. That is, current I is equal to C into dV by dt. So my suggestion is, you remember these formulas: V is equal to I into R, V is equal to L into di by dt, and I is equal to C dV by dt. So this is very easy to remember also. Just for the recollecting purpose, I have given the voltage and current relations in this particular slide, so that it will be very easy, catchy to understand what is the equivalent of series and parallel electrical circuits. In a complex electrical circuit, now if it is a simple DC circuits, means if the supply source is DC electrical source, or if the energy source acting in that particular source is, if it is DC, then that is called as a DC electrical network or DC electrical circuits. Now if the source is DC, in a complex electrical systems, now majority of the elements are resistors. Now resistors may be joined and may be seen in different configurations. Let us say if there are 10 number of resistors are there. All the 10 number of resistors need not be in series connection. Some of them may be connected in different configurations, series, and some of them may be in parallel. Some of them may be in series and parallel, like this. Now, so there may be a complexity among the geometry of connection of various electrical passive elements. So in such cases, reducing a complex electrical system having this complexity can be difficult to reduce into a simpler one. So that is why we are making an attempt to reduce the complexity of electrical networks by identifying how many of them are connected in series, and after identifying them, let us group that elements which are connected in series, and let us make an attempt to reduce all the elements connected in series into a simple passive element having the equivalent of that all the value of the elements actually. Similarly, identify how many of them are connected in parallel and reduce all the elements connected in parallel into a simplified one element, and represent the value of that element with the equivalent of how many number of elements are connected in parallel. So like this, we are going to reduce complex electrical networks into a simplified electrical network. Here, before proceeding into a series and parallel networks, as we discussed in our previous video lectures, resistors in series or inductors in series or capacitors in series carries the same current. As long as the elements are connected in series, the current is same. Similarly, resistors or inductors or capacitors connected in parallel have the same voltage across them. So as long as that elements are in series, current is same. As long as the elements are connected in parallel, voltage is same. So with the help of these basic thumb rules, we can proceed and we can simplify our total analysis further simpler. So let us take a simple resistor circuit, and here in this one there are three resistors are connected in series. Now how I said these three resistors are connected in series means, now if the voltage source is connected like this, let us assume a DC source, then this is the plus and minus, and because of this voltage source, what happens, there will be a current I. Now this I current will flow through R1, yes, there will be a drop of course, but coming to this particular node, now the total current, whatever the current it is received, the same current it will be diverted into the R2, because there is no drop at all at the node, because this is the conservation of charge as we discussed as per the KCL. So whatever the incoming current with respect to this particular node, now it leaves the same amount of current without having any drop at that particular junction. Now coming to this particular junction, whatever the current it takes, it will sends into the R3 resistor. Now like that will proceed. So overall, if you could observe, now from the positive plate of this battery, if you are traveling like this, anywhere the current remains same. The current will not having any dip in the value. So the total current is nothing but the current value is same. So as long as the current is same, then in this particular loop, how many number of elements are connected? All these elements are called in series configuration. So battery R1, R2, R3. So all these four elements are connected in series because we have ensured this connection, that is a series connection based on the current value. As long as the current value remains same, then that configuration is called as series configuration. So in this one, V is equal to that supply voltage. Let assume this is the supply voltage V, and the drop across this one is current I into R1. Yes, the drop across the second one is nothing but, let us assume I1. This is I2 R2 plus I3 R3. Then after that, R1, R2 and R3 are connected in series configuration. Therefore, I1 is equal to I2 is equal to I3. This is equal to a source current or supply current I. Then go back to our original equation. This is I into R1 plus I into R2 plus I into R3. Now we can take it as a common, I into R1 plus R2 plus R3. Then this is, it can be represented as a R equivalent. So this is V is equal to I into R equivalent. So R equivalent means what? R equivalent is nothing but this is the equivalent resistance of the given electrical network. So R equivalent is how much now? R equivalent is nothing but R1 plus R2 plus R3. See here, V is nothing but that is a total voltage supplied. I is nothing but the total current driven by this voltage source. VA and I are the resultant voltage and resultant current in the network. So resultant voltage is equal to resultant current into resultant resistance. As per Ohm's law, this could be the equivalent of the total resistance R1 plus R2 plus R3. So as long as the resistors are connected in series, then the total resistance, that is the equivalent resistance, is nothing but the sum of the individual resistor values. So this is about the series configuration. And coming to the parallel configuration, so R1, R2, R3 are connected in parallel to each other. Then you assume some voltage source here having a value of V, supply voltage V, and across this voltage V, one resistor R1 is connected, R2 is connected, R3 is connected. So this is the total current here. At this particular node, if you could observe, at that particular node, the current is finding two paths. One current is coming like this I, and it is divided into R1 resistor, and it is something different. So this is approaching to node B, and this is assumed A. So this current is dividing at this particular node A. So this is nothing but this branch and this branch are in parallel to each other. So this is because now just now we have discussed, as long as the current remains same, the circuit is, or the elements are connected in, the elements were assumed in series configuration. Now here in this, at this particular node A, what it is happening, then current is nothing but the changing, or current is dividing into two paths. Then this path and this path, this particular path and this path are said to be parallel, because at this node A, the branches are having different currents in it. So this particular branch and these branches are called as parallel branches. So this current will change. So the current entering into the R1 resistor is I1, and similarly, whenever this current is approaching to this node B, here also again it was divided into two different branches. So this current is nothing but the current entering into R2 resistor is I2, and the remaining one here, let it be C node. Here the current, how much is coming from B node, the same current it will flow into R3. That current is nothing but the I3 current. So here finally, is I is equal to I1, or is equal to I2, or is equal to I3? No. I1 may not be equal to I2. I2 also may not be equal to I3. So all here in this total configuration, we come across with four currents. One is the supply current I. Then the current flowing through R1 is I1. Current flowing through R2 is I2. Current flowing through R3 is I3. We don't know the values of R1, R2, R3s. So the I1 definitely may not be equal to I2. It may not be equal to I3, because as the resistors are different, voltage is same. So voltage is same, but having some different resistor. If the resistance is different, then in order to maintain the voltage as a constant, current values also differ. Now this is nothing but the conservative of energy. With this principle, what I am going to establish the relation among the parallel passive elements, and if the elements are connected in parallel, whatever the equivalent of them, and let us determine that value. So coming to this, now here it is very clear that I is equal to I1 plus I2 plus I3. That is the supply current, because I have applied KCL at any common point here, somewhere in between. So incoming current is I, outgoing currents are nothing but I1, I2, I3. See, same circuit, this can be redrawn like this. This is the voltage source, and it is having a current I, and this is R1 resistor, this is R2 resistor, this is some R3 resistor, right? These three are connected here, and this is coming back. How much of current? I current. So this current is I1 current, and the current flowing through this is I2, and this last current is I3. So at this particular node X, let us assume at node X, if you are applying KCL, then whatever the current I is equal to I1 plus I2 plus I3. So I1 is nothing but, now there is as per the Ohm's law, this can be written as V by R1, plus I2 is nothing but the V by R2, plus I3 is nothing but the V by R3. Ohm's law is nothing but the V is equal to I into R, and if you want to determine I, this is equal to V by R. But across R1, R2, R3, voltage is same. Only the resistances are different. So that's why I am writing I1 is equal to V by R1, plus I2 is equal to V by R2, plus I3 is equal to V by R3. Now V is common, just you take 1 by R1 plus 1 by R2 plus 1 by R3. So this is furtherly it can be represented as V into 1 by R equivalent. So whatever the 1 by R equivalent, the 1 by R equivalent is nothing but this is the 1 by R1 plus 1 by R2 plus 1 by R3. So this is the equivalent of 3 resistors connected in parallel. If one more resistor is added here, in addition to this R3, if you are taking one more resistor R4, then the value is 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4. Like this, you can extend the same analogy if the resistors are added. And at every time, you need not do all these exercises. Just you remember, as long as the resistors are connected in series, then the resultant equivalent resistance of the total network is equal to sum of the individual resistors resistances. Similarly, if the resistors are connected in parallel, then the equivalent is nothing but 1 by R equivalent is equals 1 by R1 plus 1 by R2 plus 1 by R3, so and so. Now this is about the resistors connected in series and parallel, and similarly the same concept it will be employed for inductors. Now here only you have to replace R with L, then that holds good. Now this is inductors connected in series. Now same, some voltage source if it is applied, then L equivalent, inductance equivalent is L1 plus L2 plus L3. So I am going to define here some voltage source. Let us assume this is a V. V is equals, and the current is same, I. Now the formula is nothing but the L into di by dt. This is nothing but it is a formula here. Now the first inductance, the drop across the first one. So here what I am doing is supply voltage is equal to drop across L1, drop across L2 plus drop across L3. So VL1 is nothing but L1 into di by dt. Why I am not writing di1? Because series connection current is same. So L2 di by dt plus L3 di by dt. So from this you take di by dt as a common. So L1 plus L2 plus L3 into di by dt. So whatever the left side value, this is V. So V is nothing but, this is nothing but L equivalent into di by dt. So whatever the L equivalent. So L equivalent is nothing but L1 plus L2 plus L3. Similarly, for inductors, if they are connected in parallel, some same concept let us apply. What we have applied for resistors, that is 1 by L equivalent is equals 1 by L1 plus 1 by L2 plus 1 by L3. Then the last passive element is capacitors. If the capacitors are in series, now this is again you take some voltage source V. So voltage across C1 is VC1, voltage across C2 is VC2, and voltage across C3 is VC3. This is the current I. So supply voltage V is equals VC1 plus VC2 plus VC3. So whatever the across the capacitor, for the capacitor, whatever the voltage relations, current relation I is equal C dV by dt, and V is equal 1 by C integration over I into dt. So just try to make use of these two principles, formulas to determine the equivalent of this. So here we want to determine whatever the VC1. So VC1 is nothing but 1 by C1 integration over I dt. Because why I am writing only why I not I1? Because this is a series network. So integration over I dt plus VC2 is equal to 1 by C2 integration over I dt plus 1 by C3 integration over I into dt. So this total value is 1 by C1 plus 1 by C2 plus 1 by C3 integration over I into dt. So this is nothing but 1 by C equivalent. Sorry. Integration over I into dt. This value is V. So whatever the C equivalent now, 1 by C equivalent is nothing but the 1 by C1 plus 1 by C2 plus 1 by C3. See, for the two passive elements what we have discussed, that is the resistance and the capacitor, for the two series connected resistances are just algebraic sum. So R equivalent is equal to R1 plus R2 plus R3 plus R4 plus R5, so and so. Similarly, for the inductors also, L equivalent is equal to L1 plus L2 plus L3 plus L4, so and so. But for the capacitance, that is different. That is 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Now, if the capacitors are connected in parallel, now for the understanding, we have taken 3 again. So, here the input current is I, this is I1, this is I2, and this current is I3. Same, like this is the current I, and this is the one capacitance I1 current, and this is one more capacitance I2, and this is one more capacitance I3. So all these threes are connected here and coming back, and there might be some electrical voltage source. So as per KCL, you apply KCL. Let us assume this is a node some M. At KCL at node M. Then incoming current is I is equal to outgoing currents are I1 plus I2 plus I3. 3 currents. So I1 is nothing but just you go back to this formula. I is equal to C dV by dt. So I1 is equal to, capacitor is different but voltage is same, C dV, C1 dV by dt plus C2 dV by dt plus C3 dV by dt. So the equivalent is C1 plus C2 plus C3 into dV by dt. So this value is nothing but the I. So this is C equivalent into dV by dt. So what is the C equivalent now? C equivalent is nothing but the C1 plus C2 plus C3. See, for the resistors and inductors also we have calculated if they are connected in parallel. But there we got a reciprocal of 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. But here the capacitor values are different. Now try to remember the formulas for various passive elements. If they are connected in series, what it will be the equivalent, and if the passive elements are connected in parallel, what will be the equivalent of them. We have established the relations between V and I, and after that we have simplified and we have reduced if an electrical network consists of more than few elements and connected in series or connected in parallel. And in overall, this is the slide. It speaks about resistors, inductors, capacitors if they are connected, and same if they are connected in parallel and series. So this series and parallel connection highly helpful for us to reduce a complex electrical network into a simplified electrical circuit, and finally we are going to equate, or we are going to represent the equivalent of the elements connected in series and or the elements connected in parallel. Thank you very much for watching this video. Thank you very much. In the forthcoming videos, we are going to discuss about various reduction techniques, electrical reduction techniques, that is nothing but the star delta, delta to star, and voltage divider principle and current dividing principle, etc. etc. Thank you once again. Thank you for watching and subscribing this channel. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.